Dave McAllister, as the thing says down at the bottom. A little bit about me. I work for a company called Splunk. I've been there a grand total of 3 months. I've worked in a number of different disciplines, a number of different vendors. I've helped build some of the largest IoT environments in the world with middleware messaging. I am owned by 3 cats. I understand how to take rejection, for instance. I spent 10 years as a soccer ref. I know how to be argued with, trust me, on this. I'm married, therefore I don't read minds. If you have questions, you need to let me know and ask them. So that's a really quick summary of me. Splunk likes to talk about how everybody has 1 million data points, and we're supposed to have fancy slides about this. I figure those 3 things say everything you actually need to know about me. So what's happened a lot is that the world has changed, and over this time frame, we've gone from sort of the monolithic database, middleware, front-end environment to this cloud-native environment. And part of that cloud-native environment has caused a couple of different things to happen. We've seen microservices come into play here. We've seen lift and shifts. We've seen refactorings where people are writing different things. With that has come a brand new level of complexity, and at the same point in time, we've got an instant gratification society where 5 seconds is a lost sale in e-commerce. So those 2 things are driving sort of the aspects of the things that we're going to talk about when we look at monitoring for this Kubernetes world, this microservices world. But we're really going to start off with a discussion around observability. So observability has been around for quite a while. It started with machine theory, in fact. And honestly, what's happened when I look at observability and look at it from a monitoring viewpoint is that people, but they don't observe. They've got lots of things, pieces of data, and all they're really looking at maybe are sort of the pretty pictures of what that means. But underneath that can be a lot of other things. The other way I tend to describe this, if you're getting into the observability piece, you want to check the depth of the water before you dive in head first, in all cases for this. So observability is a signal-to-noise problem. But it's actually not a signal-to-noise problem. It's a signal-with-noise problem. We need all of that data that's coming into here. And we can look at ways of taking that data down. Back to building hardware systems here, we had to worry about the signal-to-noise ratio quite often. And there were 2 basic ways of handling that. One, you filter it on the front end. You do a pan-pass filter, and you get the relevant data that you want inside of here, but you ignore all of your outliers. Outliers matter in observability and systems far more than the common middle ground does. The other one is you bring everything in, and then you sort it out into the things that make sense for you, and you separate out the outlier capabilities from the everything's fine type of capabilities. These 2 things deal with that, and red, which is what we're going to cover here, is the first pass method of looking at what filtering can do for you inside of these microservices environments. So after this slide, you can all leave. We'll be done for the day for this. But basically, observability is the quality of the system that tells us what's going on inside the system by looking at we can see from the outside world for that. This means a couple of things. You have to build the system to be observable. Doesn't mean you have to write code to be observable. It means your system has to have the ability to share that information. And then for engineering purposes, it really is doing that. Designing the variables so that you can see what's going on inside of your system. If you're driving a car, for instance, and the check engine light goes on, that's a piece of observable data, but it doesn't tell you much. And that's sort of the metrics viewpoint of the world here. You need to be able to look inside, see more details to understand that your oil pump just failed, your engine is overheating, and you're about to seize up. So those are where you start bringing in additional sets of information. So observability is not one-dimensional. And this is kind of where I first got started, was that people would look at this and say, oh, look at all the pretty little numbers inside of here, and we're perfectly happy because all the pretty little numbers tell us things are going okay. That's basically what monitoring is designed to do, is tell you things are going okay, and tell you when something is not going okay here. But when we start looking at this from an observability viewpoint, we actually need more data, the first set of dimensionality that comes into play here. We need the logs. We need to look at the metrics. We need to look at the traces. We need to look at events. We need to look at every piece of information we can get that makes sense for us so that we can actually determine what's going on inside of that system. All of these include metrics and time, because that's the simplified approach for what we look at. I think it's Uber. Their tracing model is 50 billion traces for every 10 minutes, and no one is going to watch every single trace. So we need to be able to aggregate up and disaggregate as we need to do it. It also needs to be crossing all the boundaries. It's not just an application issue, it's also an infrastructure issue. That's our second set of dimensions that come into play here. The first is that we have lots of data signals. The second is that we have lots of sources of those data signals. And anything that slows you down is bad. If it takes you 30 minutes to realize a problem has occurred, it's not useful. So those are the things that really break into this dimensionality picture for observability. So observability isn't just monitoring, and we'll get back to that in a minute here. It is an attribute of the system. You make the system observable, and monitoring is a verb. It's what you're doing to the system inside of here. You'll also hear about 3 pillars. We'll cover them more, but those pillars are actually made up of lots of different signals inside of here. Just in the log file information alone, you can have system logs, and you can have infrastructure logs. If you're in a Kubernetes environment, you've got the Kubernetes orchestrator logs, you've got the worker node logs, you've got the pods, you've got the containers, and you have the application. That's just the log thing. Ran into a problem about 4 months ago where one single customer in a very large environment was slowing down on their ingest. Everything else in the system was running fine. The system is 1,500 cores, and the user was using probably 16 to 20 of those cores, and was slowing down, and we couldn't figure out why. We actually had to go all the way down into the thread logs of the CPU cores themselves to figure out what was going on inside of the system. And interestingly enough, what happened was we turned out when we started unraveling this thing, which took people a lot smarter than me, 2 full days to do this, to figure it out, what it turned out was somebody had misconfigured the queue depths and failed to set the queue depths to fail over and build more queues. And their queue alone was filling up, and everybody else's was fine. So that's an indication of all the signals that come into play here. You're also going to need signals you've never thought of before. Observability is about finding the unknowns inside of our system. Monitoring is about finding the knowns of the system for here. So all of a sudden, you're going to find things that you never thought of before. I would have flat out told you 5 months ago you would never need to look at a thread log unless you were writing compilers. Guess what? I was wrong. So we do have 3 pillars that come into play here. And you'll see them as metrics. Do I have a problem? This is where you detect what's going on inside of here. Traces, where is the problem? This is the troubleshooting aspect of this. And then finally, logs, what is the problem? It pinpoints those things. These are our 3 pillars. Those pillars can be made up of lots of different signals, but these are the 3 aspects that make up an observability space. Everything is an event. Events, traces, metrics, whatever. Everything is an event. If it isn't recorded and measured, it didn't happen. Keep that in mind. Which means that if somebody is sampling, if you're pulling a sample data out and you pull 1 out of 10, you're missing 90%. It means you're missing all your outliers. This is why sampling does not work in this environment here. Metrics, efficient beyond belief, 100 million metrics per minute, no problem inside of here. Logs, full fidelity, but it's dependent on who decided what to put in the log file. My previous company, we had an engineer who thought it was really cute to put in his log entries in Russian. Okay, none of our DevOps speak Russian. That was problem number 1. We did get him to change it. So he did. He changed it and put in English that said, "Here I am," in every single one of his log entries. He no longer works for that company, by the way here. Traces are really cool, but they take additional work inside of here. Logs are bulky at full fidelity. Traces make logs look efficient and slim. For every single set of a transaction, a log file may write off 8 entries inside of a single e-commerce transaction. The traces for that will be about 150 to 200 traces, pieces of information. And so you've now got this full fidelity aspect inside of here. And I love this cartoon because history is the fiction that we invent to persuade ourselves that events are knowable and that life has order and direction. Well, it's true. But the problem is that we are creating history every time our application goes through a request. So it's not past history, it's present history, and that's what observability shows us. So expect that you're familiar with microservices architectures, but this is an example of a microservice architecture based off of the Amazon ordering page alone. It's a little out of date. I haven't updated it here, but you can count real quickly. There are 3, 5, 8, 10, 11 separate microservices just for the order page alone. By the way, this isn't actually fulfilling the order. This is just that page has that many microservices attached to it. Expand that times the number of people that are making use of this. Add into it the back ends, credit cards, currency exchange, fraud checks. All those different things become more and more. It is easy that something like this page, once it's completed a transaction, is going to have something around the neighborhood of 200 to 250 services it touches. Some of those are standard third-party packages. Some of those are written. A lot of those, this is Amazon, a lot of those are open source that we never get to actually see what they did to change it, but it's there as well. But nonetheless, there's a lot of microservices. These microservices interact in unique ways. And because of that, we need to be able to trace, this is where tracing comes in, the pathway that your request took as it moved through the system. Kubernetes, which is the other side. While we had microservices before we had Kubernetes makes life a whole hell of a lot easier in dealing with microservices, particularly container-based, cloud-based. And basically what it's going to do is keep track of everything that I've asked it to build, put it into the environment to which it can be built, and make sure that things are running smoothly. However, back to this complexity issue, Kubernetes adds layers of infrastructure that we didn't have to worry about before. You've got the orchestrator itself, you've got the worker nodes, you've got pods, you've got containers, and you've got apps. We used to just worry about apps and servers. And then we worried about containers, apps, and servers necessarily being virtual inside of here. And now we have multiple pieces. And we have to worry about it because Kubernetes is built to be failover capable itself. So we've got to worry about multiple master-slave relationships that happen inside of that at the same point in time. There's a control plane that figures out where you want and how you want to deal with this, and it keeps things running smoothly. What that means is you need to observe all of those pieces as well, not just your application, but the control functionalities that deal with that and all the infrastructure pieces. This is important because it's ephemeral. Things are not always there. And honestly, unless you go figure out where it is, you have no idea where Kubernetes puts something. You can tell it what kind of things to put, what systems you're looking for, but you don't get to say, put it on server A. Only if server A is the only thing that meets the qualifications. And so we're now having to observe the state of systems that we don't know where they are until we observe them. So it's amazing how confusing this is, and I figure that it shouldn't be called, I think it should be called Schrodinger's observability, because the system is either alive or dead, but we don't get to know until we look at it for that. So observability, and I think this is my last slide to talk about observability, is actually a loop problem. In machine theory, I used to build process control software for plants that automate and run themselves. There are two aspects of observability. One aspect is what is it doing? What can I see? And then the second aspect is called controllability. The way that we get data in and out is called telemetry. And then in machine theory, those are the three pieces that make up this cycle here. Observability is the ability to see these things, and it's made up of that log, traces, metrics, and whatever. We need to close this loop. Observability needs to have a closed loop here. And that loop closure can be automated so that the system itself knows how to fix things. You release a new microservice. The microservice causes errors to show up someplace else. The system can roll back to a less known stable state automatically for you. Or it can say, oh, great, look, there's a problem. Let me send an alert out, send out a Slack message, have somebody's phone go off, and have them look at it. And that's an open loop. But both of them complete the loop. This is something that's missing when we tend to talk about this space, is everybody looks at this as a see something and say something problem, where it should be a see something and do something problem for that. So why Red? Why Kubernetes inside of here? Complexity matters. We have a lot of complexity that actually makes our life easier, but not simpler inside of here. There are lots of moving parts. There are lots of interrelations inside of here, and there are lots of things that aren't there when we go to find out what happened. Again, in a Kubernetes space, if a pod dies, every piece of information it has had about what was going on in that pod dies with it. Unless you take the action to save it off, you will not know what happened to your pod. And so you need to be able to make sure that that's going on inside of that. We need to have simplicity to help reduce some of this clutter. Again, this is not filter on the front end, filter on the back end for that. And then we need to be able to retain that complexity so that we can drill into it. You can think of this in terms of aggregation. I'm going to aggregate things together to something that makes sense, but when I need to, I'll pick it apart so that I can find out what was inside of it that made up that set of information. Excuse me, real quick. There's the other headache. I think I was never had any allergies until I moved to California and the trees started blooming, which means that I sneeze between January to June and then October to December, very honestly here. So what is Red? Red is actually a subset of Google's SRE environment called the Golden Signals. And it's really originally built by a guy named Tom Wilkie, who at that point in time worked for Weaveworks. And it's made up of three topics: rate, errors, and duration. And you can actually break this down and go, rate is metric, errors are logs, and duration is tracing. But that's oversimplifying in some ways here. He originally designed this for request-driven microservices. But it actually turns out it works for anything that is request-driven. It doesn't have to be microservices-based, which means that if you have a standard environment that has a request that you can track, and it goes through and comes back, you can run a Red environment against that. And as you can tell, what happens is I have over here my microservices. I'm showing the request rate. So this one is running almost about 10. I'm showing an error rate, which is currently at 51% for that one. I think there might be a problem here. And my duration is broken into two aspects. I'm showing the percentage at 50, and I'm showing the percentage at 90 inside of that. That information alone gives me an amazing amount of information, but not enough. Very honestly, I can say there is something wrong going on here. 51% error rate's a little bit off the extreme, but it's not time-based. And so all of a sudden, I've got those two pieces inside of here. And as I look down, I can say, oh, well, maybe there's something going on here. There's a 29% showing up in catalog, and there's a 55% showing up in payment. So now I can start drilling in to figure out what's going on inside of those things. But Red is the ability to take all that massive amount of data from all those different pieces and run it into something that you can very quickly determine whether you have an error and where the error exists. Think of it this way. Red is monitoring at Chuck Norris level. Chuck Norris took action. He didn't just see things, he actually did something with it for this. By the way, that joke does not work in Spain, but it does work in Japan, interesting enough here. So again, metrics, logs, traces make up this rate environment here, and it gives you both the recognition of issue and the recognition of the root causes that take part inside of this larger environment. So rate, very simple. how many things are flowing through the system. You can think of this in terms of bandwidth, overall bandwidth. You can think of this in terms of individual calls, be they HTTP calls, SOAP calls, REST calls, API calls, whatever one. You can break it down into any way you want to look at how many things are going through your system. Very honestly, to quote John Massey, very famous computer scientist from the 90s, bandwidth costs money. And so knowing this gives us the ability to look at what our systems overall are doing. You can actually use this in anything that can fail on bandwidth. So if your bandwidth shoots up high, you may have a problem. Maybe you need more systems. If your bandwidth suddenly goes to 0 and it's Black Friday and you're Amazon, you have a different problem. So your bandwidth your rates can measure both directions going on here. Quick example, 10.3 request. I can see what my request rate works at in this particular model. It's a 10-second model. I can see where the endpoints are, what endpoints are making the most requests that are going on inside of here, and I can break it down by endpoints that go into each of those pieces. I can actually, again, take a red environment and build out more and more information. Again, I've got the underlying structure, even though I'm starting with a number that says 10.3. I can now disaggregate to get more information out of a red environment. Errors, everybody kind of knows what errors are. Something that gives me an incorrect, incomplete, or unexpected result. That's an error inside of here. And it can be lots of places. It can be something that's wrong in code. It can be something that's wrong in infrastructure. It can be peak load. It can be communication problems. One of the worst possible scenarios is when you have two of those that hit you at the same time. That will still show up as errors. And again, you'll have to be able to disaggregate to get down to what's going on here. Errors are the thing that need immediate response. Literally, in the time I made that statement, you probably need to figure out what's going on with errors and get back to a stable state somewhere inside of your environment. You can't necessarily sit around and wait for it to happen inside of that. It needs deep diving. It needs high fidelity functionality, because you're going to want to go right down into the specific spot and the specific report of what went wrong with that system inside of here. And reflecting once again, it's now. There is no tomorrow when you're dealing with an error. One of the lines I do like to add here, because this gets brought up, is that, oh, we catch all these things in testing. Sorry, testing for production is not running in production. Prime Day of 2017, Amazon spent 5 hours not able to process orders. They rolled out a new service that was supposed to be able to deal with an elastic expansion of the order system on Prime Day, which passed testing just fine and failed in production because they didn't expect the volume of traffic to hit them in the first point in time. By the way, that's $386,000 per minute of lost revenue. 336, sorry. So errors are usually reported in error rates. Again, so I can look and see I've got a percentage of error rate that's happening inside of here. The error rate that's happening reflects back to your rate, how many things are coming in. So if I've got 10 things coming in, 4.5 of them are failing. Since it's averaged out over 10 seconds, it varies across here. But again, I can look at its rate over a very tight time frame. I can look at it from endpoint, and I can drill into any particular point by simply drilling down into that error logging type of information that's going on. And so one of the things that's useful is where you can step into it, click on a dot, and see specifically what its pieces of information are. And duration is all about time. And this is the realm of distributed tracing. These days, with CNCF, we have open tracing. We have the outside project from Google called Open Census, and we have the new Sandbox project, which combines open tracing and Open Census together to become Open Telemetry. Open Telemetry provides all those aspects, APIs, plus the metric-defined environments, plus the ability to hand it off to tools to actually show you what's going on inside of here. Its job is to bring things into order. That's really what its job is, and to tell you how long things took. Now, that headache used to be that distributed tracing required you to re-instrument your code base. But now we have a lot of techniques that allow us to look at what's going on inside it, because one of the major portion is between the service endpoints. And so we need to be able to measure the points of communication, which is in the network phase. You'll hear a lot about service meshes, Istio, Envoy Proxy, Linkerd, all those different pieces provide that information. And every one of them provides you a distributed tracing environment pretty much out of the box. You can also use instrumented libraries, not touch or code, but instrument the library that allows you to see what's going on there as well. What it does is tells you what happened in the event, how long it took, somewhat to a point of why it took that long, and then what microservice or service was responsible for the delay. In a microservices environment, quite often when we see errors, they have nothing to do with the service that reported the error. Quite often they are somewhere else in the environment. And tracing will help you figure out where the original backtraced error came from, so that you can start narrowing in on the root cause as fast as possible. Duration examples, again, you'll see them usually as an aggregate number. You'll bring them up. Again, this one's a 10-second example for this. The aggregate number then shows you out to the distributions, which then can show you out to the endpoints. The other thing that tracing will do for you is show you what's called a service map. It will show you the process, the mapping of where your actual request went through your system. So imagine, for instance, you are, again, a big e-commerce shop. You've got lots of front ends coming in here, each of those generating a request. That request goes to some collection, elastic or not, of services. And you need to be able to trace through what happened for that specific request, because, again, the infrastructure matters to the application as well. So why red? Well, red's easy to remember, very honestly. It also, we found, when I was doing consulting, we found that it's easy for teams to agree to start with red. It's a common language. It's a very simple method to be able to say this very complex world can look like this, and then we can expand to figure out what else we need. In a microservices environment, again, teams don't work on all the microservices. Individual teams will work on multiple pieces of those microservices environments. And red gives them that common vocabulary to say, hey, I saw an activity that the rates went down here, and I saw an error here, and my duration went screaming up around here. And everybody knows what it means. And so it provides a common language here, a consistency that crosses multiple teams and multiple geographies. The other thing is that since red is a fairly well-defined environment, you can automate around it. When a red alert occurs, you actually know what the red alert means. And so then you can start doing automation. Red alert happens. Look and see what happened inside the system. Look and see if there's been a new deployment of a service here. Roll back the service. All those things are automatable. All those things are managed, can be managed, even if they're not automated, directly through runbooks. And so we can get the response aspect, the respond aspect of your system, returning stability out faster with a red place environment here. And interestingly enough, it serves as a proxy for user happiness. Users really are interested in, did my request make it through, and did it happen in time? E-commerce, 5 seconds is a lost sale. 10 seconds, he was somebody who will go complain on social media or to their friends about how slow you are. So a Google study from 2017 pretty much defines it that way for here. So if you look at this and you start looking and seeing what your rates are going through correctly, your timing is going through correctly, you probably have happy customers, at least with your applications. Pricing is somebody else's problem. So here's the downside. This looks really cool. Rate, error, duration. I've only got to worry about 3 things. But every one of those pieces can impact something else inside of this picture. So I have an error. The error is causing me to have, I'll pick on the infrastructure. I have a flaky network card. The network card is causing my rate to drop, my error rate to go up, and my duration of the things that are completing are fine. So even though I can figure out what's going on inside of here, each piece, I can have a high rate that is not showing me an error. I have a high rate. It's causing me a duration problem because my bandwidth is saturated. So all of a sudden, I've suddenly got a slow consumer model that's happening inside of here. So each piece can have a correlating effect that may or may not show up inside of the one that's causing the problem. And this is where red gets a little bit tricky, and you need to be able to watch and understand what the balances are. This is also why you need to always be able to show all three at the same time, because that will give you an indicator that something else is triggering this piece over here. So it's also not infrastructure, and it's not application. It's both. And if somebody is looking at this and saying, we can tell you everything about your application, it's not going to help you. And if they say, we can tell you everything about your infrastructure, it's also not going to help you. In a red environment, in a microservices environment, these two pieces work in lockstep, and you have to be able to look at both of them here. Tools should be able to help you out here, but if all they're doing is showing you pretty numbers, don't go there. You'll spend more time setting up pretty numbers to be able to not have the data that's inside of here. Doesn't mean you can't use things that produce pretty numbers. So for instance, Prometheus is an amazingly cool metrics tool that happens to have the ability to produce red inside of here. But what you're going to want somewhere is the ability to drill into what it's telling you is causing those numbers to change. And I fully love Prometheus. I was one of the early guys who jumped on this and dragged it into companies kicking and screaming, and only one of them actually kicked me out because of that. But nonetheless, that's the model. So red can uncover, overall, the problems that are riding inside of your microservices under Kubernetes or under any other orchestration model that you may be interested in. But you need to be able to make sure that you have the ability to drill into it. A little bit of sort of the Zen of this. There are really only two views that matter to the Zen model. One of them is that external customer's view that I talked about, and they care about request, its latency, and whether it was successful. And again, if you think about this, that's rate, error, and duration inside of that. The operator's view is that pluralized. It's the requests that go in here, the rates, and the concurrency that's happening, as well as whether the errors are, and the operator cares about the infrastructure and what the infrastructure is doing. So that's sort of the Zen model. When you look at these two things, you get to be able to look at the user viewpoint as well as look at the system operator viewpoint for red. Some philosophy. I ran a nonprofit for Stanford University called Philosophy Talk. The hardest job in the world is to get two fully tenured professors of philosophy to agree on anything. Even if they are in complete agreement, they won't agree. I mean, it's painful. But nonetheless, so I always throw some philosophy in here. So instrumentation is not the answer. It may help you find the instrument. Just because you instrument doesn't mean that you're going to magically find out what's going on inside of here. Metrics are powerful. Don't live without metrics, but they're not sufficient. You've got to be able to drill into this. Cardinality matters in this space. The ability to slice and dice and find new pieces of information. In fact, remember, we're looking at unknown unknowns inside of here. So we don't know what we're looking for until we have to go find it. So cardinality matters in this space here. You also want to look at the work that's going on, not the service, but you're going to watch the service anyway. But when you're looking at the service, think about how it works in relation to the work that's going on inside of that. And your goal is not observability. Your goal is reducing the mean time to detection, the mean time to respond, and the mean time to resolve any underlying problem. That is my final philosophy statement here is, the observability is not the goal. Observability is a method of reaching that goal. So observability is more than monitoring, but it starts with monitoring. Everything starts with monitoring. If you can't see it, it didn't exist for that. Red wins on microservices applications because it gives us a common environment. It lets us cross those boundaries. It lets us look at all the pieces of information we need to determine that everything is working right, and when something isn't working right, where it's not working right and why it's not working right as fast as possible here. Red particularly simplifies Kubernetes while letting you still have the insights that are necessary to make this job happen here. And keep in mind that those red sections interact in ways that may take a little bit of experimentation to determine exactly what is causing that functionality to happen here. And finally, find the right tool. It doesn't mean there's a specific tool. I wouldn't recommend one. If you want to start with a standard model of 3 environments here, you can go grab a Prometheus environment, you can grab a Zipkin environment, and you can grab whatever your favorite log tool is, grep, whatever. And it will give you the same functionality. But the tool will help you get to the results faster if it all works together in one place. And with that, I'd like to thank you for your time, and I've got you 35 minutes. Wow. So, and at this point, we can maybe make a happy hour. So, for this, questions before I get off stage? Yes. So tracing, we've been tracing for years, very honestly, for that. So yes, so there is the concept of tracing that, for instance, has lived inside of machine code for years for this. Distributed tracing is the ability to extend that trace across multiple systems and multiple boundaries. That's really what it comes down to.
That's how I think. I just want to make sure.
Yep.
And then to find the right tool, we often talk about having a toolkit.
Yes.
Talk about finding the right tool just for a specific piece of observability?
So you're correct in that there are a minimum of 3 tools. And yeah, my company has a set of tools inside of here, but it is not my limiting factor when I go to a customer site environment for this. For instance, my company doesn't offer Prometheus, but I make sure that if you are interested in Prometheus or you have a specific use case that Prometheus meets really, really well, I want to be able to pull it in. The integration of the tools matters. Okay, it's like it's sort of using car analogies again here. It's sort of the difference between having a socket wrench and having a set of box-in wrenches. A socket wrench, I'm going to be able to pop in and out and find the right piece I want. It's a smaller, more complex concrete piece here. I have a full set of box wrenches because if something strips, the box wrench is magic for making that happen. But I've got to go dig through and find the right one. So yes, it is a tool chain. It's actually the way I prefer it versus a tool set.
Thank you.
Sure. Questions? If not, I'm going to give you 20 minutes back of your life. Thanks for coming out and listening to me. And enjoy the rest of the show.